Hey, my name is Julian Rojas. I'm currently pursuing my PhD at TU Delft in the Netherlands, and today we're talking about sustainable transportation. Transportation is one of the biggest players as a contributor to greenhouse gas emission and a key driver of climate change. For instance, here in Europe, it accounts for approximately 20% of the greenhouse gas emissions, making the decarbonization of this sector a pressing priority. Among the various modes of transport, rail highlights as one of the most sustainable ones, and here in the Netherlands, you can use it for commuting to practically everywhere within the country. Despite its relatively low carbon footprint, the railway sector is under constant pressure to further reduce emissions in alignment with carbon neutrality targets set by government and industry stakeholders. These targets represent both an environmental necessity and also an opportunity to displace fossil fuels as a dominant source of energy and to embrace energy transition. As urbanization accelerates and mobility demands increases, the load on distribution system is expected to reach critical levels. Unfortunately, congestion problems have become a global concern nowadays, not only for transportation, but also for industry and residential consumers. This could also affect on the train schedules, where operators are forced to dynamically adapt the energy demand of the trains to avoid potential fines. As a consequence, there has been an increase in interest in local energy generation, storage, and management solutions for rail-based means of transportation, aiming to reduce public grid dependence and enable future expansions. However, how to integrate and standardize or control or manage these kind of assets in the current electrical infrastructure are open questions that we aim to tackle. So this work presents an optimization problem for minimizing the overhead lines losses. We want to study and evaluate how a storage unit can be used to provide power to the system, but at the same time, by dynamically adapt the voltage within a specific point of the segment, will minimize the conduction losses along the overhead lines. So the formulation of this problem can be very sketchy and hard to manipulate. Also, it derives into a nested function, which cannot be solved analytically. Therefore, it has to be computed numerically. So we propose to approximate the previous set of functions with a more simplistic version that allows us to manipulate the expressions with algebra, while keeping the quadratic dependency on the key elements that describe the system. Our results confirm that the simplistic version of the system model can be used for solving the optimization problem, keeping acceptable values for error, especially for short distances. Finally, we would like to thank IEEE IS students and Young Professional Paper Assistant Program for allowing us to participate and share our research among the community. Thanks.